The first paper will be Sendhil's paper with Ashesh, and it'll be discussed by John McHale. So Sendhil, over to you.
All right, thank you very much. I'm just going to jump right in. This is with Ashesh Rambachan. It's Science in the Age of Algorithms. I think this is something that doesn't need much motivation. I feel like if I was to use a canonical example, AlphaFold has really been an example that has motivated many people to think that algorithms, AI, whatever you want to call it, can have enormous power in science. And so what I want to do here is I want to take the transformative charge and kind of step back quite a bit. And the way I want to do that is I want to use a possibly inaccurate, but I think largely accurate story from electricity. The story goes that when electricity came, its productivity benefits were not felt as strongly immediately. And that was because it took some time to absorb electricity. To get this, the physical nature of steam power is that there's a big thing producing energy. And so the factory had to be laid out around the big machine. When electricity came, they just replaced the steam power with wires. That had some benefits. But the real benefits came when they said, wait, I can actually move the machinery any way I want. And so the entire factory floor changed, and there were big benefits. That's the metaphor I want to carry through today. What was true of electricity and manufacturing, I want to argue that the big benefits from science will come not from electrifying, but by fundamentally changing the factory floor for science. And this was an interesting exercise for us because to reflect on what is the current factory floor required a lot more stepping back. And that's a journey I'll try to take you on today. To do that, I want to start with what I think is the default view that was in the back of my head of what the factory floor of science is. And it's probably what we all think of when we say the scientific method. I'm going to call the scientific method the reigning champion view of science. There's a science that's the best we have, the theory that's doing well. We run a horse race. And that horse race, either the best theory is supplanted by someone else, and then that's the new best theory, or that's Kuhn, Popper, however you want to think about it. The sort of reigning champion view of science is what I want to take as my default view. And it's the view I think I have in the back of my head and many of us have. And I will argue this is a good factory floor, that is, it's an effective factory floor for some sciences. But it's a terrible one for many others, including economics. And what I want to argue is that AI is not going to disrupt the factory floor because it's a technology in and of itself. It's going to disrupt the factory floor because the factory floor was simply not working for a whole host of sciences. It was an incomplete description of the act of science, but like with many problems in life, you kind of ignore the problem if you can't do anything about it. And I think we've ignored this problem for quite some time. I hope to convince you that this is true in economics, but I also hope to convince you this is true in a wide variety of other sciences. So the way I'm going to do that is I'm going to start with some provocations, and then I'm going to describe, based on that, what I think the new factory floor will look like, and then talk about what we need to get there. Great, so let me start with some provocations. So the provocations are each going to take apart a part of the reigning champion view of science. So the first part I want to do is, well, we're running these horse races. Where does the other horse come from? We've got a theory. We know how to deal with it. Where on earth is this other horse coming from? You'll notice this is kind of an interesting problem to dig into. So let's go to something that I think we all know. Let's think about the evolution of expected utility theory. So expected utility theory, beautifully formalized, beautifully axiomatized. Then prospect theory showed up. That other horse arguably, quote, won. It had many predictions, the others didn't. And now, since then, we've had a few more theories, and they're still bubbling. Where are these coming from? It's like super smart people just being clever. Well, let's dig in a little bit. I think we can actually take apart where they're coming from one by one. After expected utility theory, a sequence of things happened, the most noteworthy of which it began with the LA paradox. LA said, hey, this is a really nice theory. Here's two menus. And if you look at these two menus, in menu 1, people choose lottery A. In menu 2, people choose lottery B. It's like, yeah, that seems intuitive. It said, unfortunately, that's inconsistent with the axioms of expected utility theory. Then there was something called the common ratio effect. And then Kahneman-Tversky in 1978, a whole host of these anomalies. And that is what kind of led us to prospect theory. But things went on, you might not have followed. There was a whole host of other anomalies, and that in turn was what led to the modern day new theories that are still being developed. My point here is that the process by which this new horse shows up is actually quite a structured process. It's the process of what I'm going to call anomaly generation. I'm going to describe an anomaly as a minimal example that a theory cannot fit. Anomalies are fantastically interesting things. Their smallness gives us a clue into what they are. Think of when we think of empirical work, we say, I had a huge data set. LA said I only have 2 data points, 2 menus. Also, I never bothered to collect the data because it's so obvious what's going to happen. So many of the great experiments in science have this feature. So if you just go back, pick your favorite experiment, double slit experiment. The double slit experiment is literally light through this thing with 2 slits, light through this thing with 1 slit. Carefully balanced to have the tiniest possible data. This has been true. Go back, read game theory. This is how game theory, oh, here's Nash. Oh, here's a supermarket paradox. Oh, Zelton. Oh, here. These anomalies are very central again and again in the evolution of every science, including the physical sciences. How do we usually find anomalies? How did LA find the LA paradox? Well, let's just think of what at its essence, the discovery of an LA paradox or a double slit experiment really is. We observe the world, we know the theory, we contrasted the world with the theory. LA said, those axioms seem good, my intuition suggests something's wrong, and then there's this meticulous crafting of this object called an anomaly. What's intriguing is every aspect of this is human. But you'll notice every aspect of this could be algorithmic. After all, data to predictor, algorithms are great at that. Contrasting with the theory, well, the theory is a formal object. So why not contrast intuition with the theory? Crafting, well, that seems a little fuzzier, but maybe we can work our way around it. So in this work that Ashesh and I did, what we tried to ask the question is, can we just build an algorithmic generator? The inputs into an algorithmic generator are nothing more than a data set and a theory. And what it needs to do is to ask, propose, I think if you measured at these exact 2 points, I think you will find there's a real problem with your theory that your theory simply cannot explain. So produces anomalies. It turns out this activity is doable. In the interest of time, I won't get into how we did it, partly because max min is quite scary. Who knows what that is? But it turns out these things actually work quite well. If you go back to the LA paradox and all you do is you give it data on lottery choices and you give it expected utility theory, it actually produces a large set of anomalies. It recovers all the Kahneman-Tversky anomalies, recovers the LA paradox, and produces a whole host of other anomalies not in the literature. The reason I'm telling you about this paper, and I will just unabashedly say out of sheer laziness, I'm just going to focus primarily on papers I'm working on just because that was by far the easiest option, but it is not any implication of quality or anything, but it just lets me tell the story easier. So as I look towards a new factory floor, one of the elements I want this story to suggest is that algorithms can suggest new theories and hypotheses. This thing that was off camera, oh, where did these new theories come from, can suddenly be on camera and be part of the factory floor. Great. Bring what is off screen onto on screen. I'll skip this bit because it's needlessly provocative and I have a little bit of time. So let me move to the next provocation. So here I want to take the word best in the sentence best theory. That's a funny word, partly, well, it's like really in your face. And I want to do a thought experiment. Suppose you're interested in writing a model of health insurance. How would you model it? Well, you could move asymmetric information. You could talk about behavioral confusion. You could talk about the game between providers. It's a lot of choices. Well, say you say asymmetric information. Well, you could talk, is it asymmetric information about health? Is it about willingness to pay? Is it asymmetric information about discount rates? Okay, let's say I pick health. How do I model consumers? Do I use expected utility theory or do I use hyperbolic theory? There's a ton of choices in every modeling exercise. If there's a single best theory, why do we have so much freedom to pick? Because there isn't a single best theory. Economics, like many other sciences, has not been accumulating a single monolithic theory that is somehow the right theory. We have been accumulating a collection of theories. For example, I said, oh, we've seen how EU has a bunch of anomalies. I am confident that many of you, all of you who have written a model with choice under uncertainty, probably wrote an expected utility model rather than writing prospect theory, even though you've seen all those anomalies. We don't view failure as determinative. We should shelf that model all around. We'll always do prospect theory with hyperbolic discounting. We've been collecting these theories because we're a patchwork science. Many sciences are patchwork sciences. It'll come to surprise you. For example, we've recently started some work on chemistry, and chemistry is actually a patchwork science. Quantum mechanics is just too ill-determined at the level of aggregation that chemistry operates at. And in fact, chemistry is a collection of local theories, such as protonation, EAS, which, like us, chemists use human intuition to make predictions of. And it's not just chemistry, solar flare prediction, medicine, astrophysics, biology. All of these fields lack a monolithic theory. They are collections of patchworks. So the second thing I want to do is to argue for you that the notion of a best theory is misleading. And we know this, like we don't have a best theory. So let's take apart the other thing, the word apply. I really went overboard with this animation. That's clear to me now. I have regrets. I have many regrets. So let's go back to this thought experiment that I talked about. When you made these choices, and if someone makes them in a seminar, and I made a goofy choice, you know what people say? How would people tell me you made a stupid choice? What would they say? How do you make this choice? Well, we use this phrase, first order. In this case, this is first order, which seems like an abuse of calculus. But I think what people mean to say is, this is important. I know this to be important. Where does any of that come from? On what basis are we saying that? It's because the testing of theories is not an isolated experiment, such as a double slit experiment. In the patchwork sciences, every application of a theory is revealing to us about which theories seem to give us more leverage where. So we are not simply accumulating the best theory. We are not doing it through controlled experiments. Application is not a secondary activity. Application is not a second-class citizen that happens after we've built theory. Now they've got the right theory, we're just going to go apply it. It is through application we learn a very valuable, in fact, the pivotal piece of information. I will just, well, if you want to talk to me, I will walk you through this. I would argue this is actually true of physics as well. I'm happy to talk you through this. I've written it down in some ways that electricity and magnetism and thermodynamics actually came from application rather than the other way around. And Newtonian mechanics is a push. But I agree, it works for quantum mechanics and relativity. But we'll skip that. I think I'm just being exceedingly provocative because I haven't gotten much sleep. So the final element of this that I want to push on is the word theory. It's going to happen again. Oh, my God. Is the word theory. And to take apart the word theory, what I would like to do now is to ask, what is a theory? Well, I think in economics, we all go back to Samuelson at some deep level. What a theory is, it's a precise formalism where the derivations do all the work with counterintuitive implications. I mean, that's what would make fantastic theory. So then I did a little experiment. I went to a bunch of people and I said, what is your favorite theoretical idea from economics? I'm going to put like what I often hear, but you might have some favorites. But people love opportunity costs. People love the prisoner's dilemma. They love the market for lemons. These all have an interesting shared component. They all involve noticing an aspect of the world you didn't notice before. And they apply to many different things. But if we're being honest, they give you just a single insight, and in fact, the insight is in the name. It's actually not that hard. Opportunity cost is not hard at all. So we have this tension between what we think of as theories, but also what we prize as theories. Objects are qualitative. Not much derivation. Their strength is in their breadth. So I might almost say there are two categories of theories. Burrowing theories, which you make a precise formalism, you derive, get something. And sprawling theories, where they seem to bind to many things and give you lots of insights. So, final element of the factory floor is I want to argue that we have to think hard about qualitative theories. For this, I'll make a sideshow. I love this paper, so I plug it everywhere. If you have not read this paper by the physicist Eugene Wigner, The Unreasonable Effectiveness of Mathematics and the Natural Sciences, you should read it. It's fantastic. His argument is something like this. He's meeting a friend who, it's about two friends who are meeting, one of whom is a statistician, and the friend says, so what do you do? Oh, yeah, well, I'm able to say whether people like soap in this area. I said, so you talk to everybody? He said, no, I only talk to some of them. It's like, how can you do that? I said, well, just like if I get just enough people. He's like, that sounds weird. And then he says, fine. What's this number here in this formula, this thing? I said, pi. He's like, what's that? I said, in grade school. He said, now you're just messing with me. What on earth does the circumference of circumference of the circle have to do with whether people like soap or not? And Eugene Wigner's point is that is the strangest thing you've probably ever encountered in your life. Why did pi show up in the central limit theorem? And he then goes on and says this happens in physics all the time. One way of thinking about the success of physics, according to Wigner, is that mathematics has a remarkable inductive bias towards the physical laws of physics. One way of thinking about our problem with qualitative theories is mathematics has not proven to have the same inductive bias as, say, language or other media. And so what I want to argue is mathematics is a language of theories because mathematics is interpretable, but algorithms do not face this constraint. And we have the ability to think and rethink what should the language of theory be, and so what should the new medium of theorizing be? So to take it all apart, putting those provocations together, I want to propose that the new factory floor is very different. It's one that recognizes accumulating understanding and using understanding are in a two-way street. They're deeply connected. What we are accumulating is a patchwork of theories, like this, in some format that we have to learn and understand. The other thing we are accumulating is the question, which theory where, which I want to argue could just be an ML model that is something we're very familiar with, which is a foundation model. But in this case, it's not a foundation model for prediction. It's a foundation model for answering the question, given context, what theories are most relevant in this context, which is, after all, what we mean when we say first order. But that is a very automatable activity. Second, because it's a two-way street, notice each deployment of the foundation model improves our ability to answer this question, and that is a two-way street. The second component I want to argue, the last component, is to argue that every time we use a theory, we have the potential to expand the theory. What do I mean by that? In any application, we should just contrast the theory with the pure black box ML model. Why do we do that? Well, because we can answer the question, does the black box ML model find some predictable emitted signal? And if we can answer that question, we can then convert that predictable signal into a new theory. That's what we saw with the anomalies thing. That's the contrast of these two things. So this is what I want to argue is a new factory floor. What do we need to get there? This will be the last things. First, I want to argue we need people, and it fundamentally needs people, even well, maybe not the full limit of transformative AI, but in my rendition. And the reason I think it needs people is because fundamentally algorithms and theories live in a data frame that they can model. The interesting thing about humans is we appear to see things not in already decided data. I think this needs theories because theories are the thing that gives us formal bridges across data frames from high to low data environments. And what it requires is a new kind of AI. It requires AI that has better capacity to develop and communicate the world models that it's finding. I think that's what a lot of AI people are trying to produce, and I think that's one of the things we'll need. So let me conclude this by saying, I think I've given you a whirlwind tour, along with changing font sizes, of the new factory floor. Let me just conclude with a quote from Bertrand Russell, which I find very interesting. In a nutshell, he says, if you ask a mathematician or a mineralogist, what body of truths has been ascertained in your science, they'll give you some very precise answer. If you ask a philosopher, which he was, they'll say, I don't really think I've got anything to say. And then he says, why is this happening? He says it's happening. He has a very interesting theory. He says it's accounted for by the fact that as soon as something becomes definitive, actionable, we stop calling it philosophy. And the philosophy is that thing of working in such a nebulous space that suddenly, when it becomes tangible enough and concretized enough, it now becomes its own field. Those transition moments from philosophy to out of philosophy are very interesting to me, and I think we're about to have one such transition moment. That transition moment is, I think, philosophy of science, which has always been in this nebulous area, is suddenly going to become an engineering activity. And the building of the new factory floor will be the engineering analog of the philosophy of science. All right, thank you.
Thank you so much, Sendhil. It's actually just an incredibly thought-provoking paper, and really enjoyed it. This is not mine.
That's mine.
It's yours.
Your time is up.
My time is up. He set the timer. So the discussion is actually joint, believe it or not, with our chair and Alex Otel, but I take full responsibility for the slides. And to say, to begin with, a remarkable sort of feature of Sendhil and Ashesh's work is that they are both involved in sort of building AI algorithms for doing science, but also able to step back and really think about the broader implications. And this particular paper is very much in that sort of philosophical mode, and I really enjoyed reading it. Now, he went a little bit beyond the written paper that we saw, so this really focuses very much on that written version. And I really see it as doing two main things. One, really asking the question, what does the arrival of this new class of intelligent agents tell us about the existing factory floor? And then the second question, which Sendhil very much focused on in his presentation, how might or should the factory floor of science be reorganized given this new class of intelligent agents? So in the paper, they go through the existing factory floor of science, and very convincing description in terms of theory, test, and use, but then look at various things that are happening off-screen or off-stage, and it's kind of useful to go through that. So one thing that's really come out, I think, of Sendhil's work is the whole process of hypothesis generation that can be seeing new patterns in the data or seeing anomalies or surprises that generate these new hypotheses. This is typically not part of the sort of the formal description of the factory floor that we see. Going back to a theme from earlier this morning, and that is tacit knowledge, another thing that these algorithms have revealed is the importance of this tacit knowledge. You know, how we map from our symbols, whether it's in the form of words or mathematical symbols or diagrams, to meanings in the world. And I think it's the failure of symbolic or good old-fashioned AI partly has revealed the importance of this tacit knowledge. Another thing they emphasize in the paper is what's happening off stage is developing sort of new concepts or constructs and associated sort of measurement instruments, again, typically not focused on in our more formal descriptions of the factory floor. And then there is something that in a sense is more negative. One thing algorithms have allowed us to see is what can be predicted sort of from the data. And how often our theories actually predict sort of very little. The R-squareds are low in terms of the overall variation under dependent variables. But I think it's also revealed that we sort of cling stubbornly to the need to have these causal explanations. And I think this is kind of stepping back. This is one of the things that we can get from this AI revolution, allowing us to kind of step back and think about how things even work at present. And for me, one of the lessons I take away as an economist, that we don't think enough about sort of the cognitive side, because many of the things that Sendhil describes here are cognitive processes. Another celebrated view of the factory floor, which I think is very much aligned with what Sendhil is talking about, is Richard Feynman's view. I won't read out the quote, but really, the thing that's kind of happening off stage is the hypothesis generation, or what he actually called guessing. So to give these offstage elements or off-screen elements a name that we have used in our own work, it's really bringing out the importance of a term that's used a lot in philosophy and in cognitive science, but not in economics, and that's abductive inference. But for us, I think we can really kind of think of it effectively as causal judgment. And it goes back to the American philosopher of the late 19th and early 20th century, Charles Sanders Peirce. That, believe it or not, is actually how you pronounce his name. And I think this really is very much aligned with what Sendhil is talking about. So he defines abductive inference as, you see this surprising fact C. If A were true, C would be a matter of course, hence there's reason to suppose that A is true. So in instance, this is a third form of inference beyond deduction and induction. So we can think of deduction as deriving the logical implications of sets of assumptions and axioms, induction as generalization from observations. For economists, we can think of the abductive step as how we choose those assumptions to begin with. And this is a really difficult problem in that it involves search over a potentially vast space of combinations of assumptions. Somehow, human cognition is able to do this. It's actually somewhat of a mystery to cognitive science itself. And I think it is what AI is struggling with. And maybe not everybody here will agree with that. But if we were to pick out something, if we were to think that AI is going to continue to be a tool for science and in other areas, it must be something that will remain robustly in the human domain. I think if you were to pick out one thing that's most likely to stay in the human domain, maybe not indefinitely but for some time, it is this ability to do abductive inference. So then the second part is, given that we now better understand the factory floor and what's going on off screen, how should the factory floor of science be reorganized given this new class of intelligent agents? This is a quote from the written version of the paper, but and again, I won't go through it all because of time, but effectively the kind of world modeling that we do as humans could be done by machines, not alone, but having a very substantial role. And I like to actually relate this back to something else I think that Sendhil is famous for, this distinction between Y-hat problems and beta-hat problems, or prediction problems versus causal identification problems. And I think a lot of what's motivating Sendhil's dissatisfaction with the current factory floor is that our theories seem to explain so little of what is apparently explainable as revealed by these prediction models. So to give a symbol to what I think he's looking for, it's something like this that would have the predictive power of our prediction models, but also allow for causal interpretations. So I think that is what he would like the new factory floor to look for. But now just to kind of push a little bit, it does, his vision, as really set out in the paper in particular, does seem to involve quite a lot of outsourcing to the algorithms. Just to look at the last bit there, memory is not stored in researchers' intuitions, but is stored in the model itself. Now, there is definitely continued roles for humans, and Sendhil talked about humans and the algorithms working together. And in particular, he sees a role for humans in developing new constructs and measurements associated with those constructs, which are indeed very important. But you could think of the human as now kind of nudging the model along a little bit. Maybe that's a little unfair, it's more than just nudges. But I think there is quite a lot of outsourcing involved. So we're going from world models in the head to world models in the system. Maybe there should be some brains in that system as well, but there still is a substantial transition. Is it feasible? At the way AI is progressing, I definitely wouldn't rule it out. But I would say that we're a long way still from it. And I think some of the best work on this is actually done by Sendhil and co-authors with Kian Vafa in particular, where they show these models that predict very well are not discovering these underlying constructs. And I think there's other evidence to show that as well. So we may get there, but it will be challenging. But I want to just kind of really close by raising a different question, and that is really, how desirable would it be, particularly when there is a lot of outsourcing involved. Now, this is, you could ask, is there a trade-off, and does it matter? But to the extent that as we move to this new, I don't know what you'd call that symbol for the new world, but that certain human understanding could be lost. And does that matter? Sendhil, I think, has been one of the most articulate advocates for the idea of thinking of AI as a bicycle for the mind. At the other end of the spectrum, I don't think this is what he's advocating, is that it would be more of a self-driving bicycle. Now, what your reaction is, it could be either of those two. But I think what they're really looking for is something more like this, And hopefully the brain is still doing the steering. But can we actually achieve that? So this is my last slide. And Ajay hasn't even kind of seen this one, so this is just pure me. So I'm sure at MIT, Sendhil will be familiar with the work of Josh Tenenbaum, but he's been involved in the writing of 2 papers. One that goes back a few years, which is entitled Building Machines That Learn and Think Like People. And even though they don't use the word abductive inference in that paper, that's really what they're describing. That was what would be needed for machines to think like people. But they have a more recent paper, Building Machines That Learn and Think With People, and set out a number of requirements for this team. So you understand me, I understand you, and together we understand the world. Kumbaya. And the question is, how much outsourcing could we do and really achieve this level of mutual understanding? So I'd be very interested in Sendhil's reaction to that. And maybe just a final thought. Do we really want to move away from using the metaphor of a tool to a partnership? Are we on safer ground, really thinking of it as a tool to make sure that we don't outsource too much?
Thank you.